My name is B. Nandakishore and my roll number is 21951A04A9 and I am from ECB section and this is EDC subject. And my topic is principle of operation of P channel JFET. It is a device in which current at two electrodes is controlled by the action of an electric field at a PN junction. A JFET or J or function or junction field effect transistor or JUG FET. It is a FET in which the gate is created by reversed biased junction as opposite to the MOSFET which creates a junction via a field generated by conductive gate separated from the gate region by a thin insulator. And this is a picture of N channel JFET and this is a picture of P channel JEFT. JEFT, N channel and P channel schematic symbols, and these are made with which is the drain and source terminals of FET heavily doped electrodes of P type materials from PN junction and each side of the bar. The thin region between the two and gauge is also gauge is called the channel. Since this channel is the N type bar, the FET is known as N channel JEFT and JFET, and these are made which is the drain and source terminal of FET heavily doped electrodes of P type material. The PN junctions of each side of the bar. The thin region between the P gauge is called the channel since these channels in the N type bar. The FET is known as N channel JFET. And this is a diagram of the electron enter the channel through the terminal called source and leave through the terminal called drain. The terminals taken out from heavily doped electrons of p-type material and are called gates. These electrodes are connected together and only one terminal is taken out, which is called gate as shown in the figure. PN P channel JFET. The device could be made up of p-type bar with two type gates as shown in the figure. This will be P channel, the JFET, the principle of working in channel JFET and JFET. The current is carried by electronics, while in P channel JFET it is carried by holes. And these are diagram pictures of and symbols of operation in JFET. The PN junction between gate and source is called and always kept in reverse biased conditions. Since the current in a reverse biased PN junction, it is also it is also and it is extremely small, particularly zero. The gate current in JFET is often neglected and assumed to be zero, and this is applied voltage as shown in the figure. The majority carries the electronics start flowing from the sources to the drain. The flow of electronics makes the drain current ID. The majority carries move from source to drain through the space between the gate region. The space is commonly known as channel. The width of this channel can be controlled by varying the gate voltage. To see the effect of gate voltage on channel width and on drain current ID, consider the diagram below. The figure as shown on in channel JFET is the gate directly connected to the source terminal with when drain voltage VDS is applied and drain current ID flows in the direction shows. Since the N terminal is resistive, the drain current causes a voltage drop along the channel. This is drop reverse biases the PN junction and causes the depleting region to penetrate into the channel. Since gate is heavily dropped and the channel is lightly dropped, the width of the duplication region will mainly the by spread in the channel as shown in figure. The penetration depends on the reverse bias voltage from the figure. It can be observed that depletion region width is more at the drain side as compared to source side because near the junction voltage at drain side is more than the voltage at the source side. This shows the reverse bias is not uniform near the junction as it gradually increases from source to drain side. The depletion region does not contain charge carriers. The space between two depletion region is available for conducting portion of the channel. When reverse bias voltage is applied externally to the gate, the reverse bias will hence increase the penetration of the depletion region, which reduces the width of the conducting portion of the channel. The width of the conducting portion of this channel reduces the number of falling from the source to drain reduces and hence the falling hence the current flowing from drain to source reduces. The figure it can be observed that depletion region width is more at the drain side as compared to source side because near the junction voltage at drain side is more than the voltage at the source side. This shows that reverse bias is not uniform near the junction as shown near the junction as shown near the junction as shown. The voltage on the other side that shows the and this shows that reverse bias is not uniform near the junction as it gradually increases from source side to drain side. The depletion region does not contain charge carriers. The space between two depletion region is available for conducting portion of the channel. When reverse bias voltage is applied externally to the gate, the reverse bias will increases the penetration of the depletion region, which reduces the width of the conducting portion of the channel. When the width of the conducting portion of the channel reduces, the number of electrons and electrons flowing from the source to drain reduces and hence the current flowing from the drain to source reduces. The figure it can be observed the depletion region width is more at the drain side as compared to source side because near the junction voltage at drain side is more than the voltage at the other side. This shows that reverse bias is not uniform near the junction as it gradually increases from source side to drain side. The depletion region does not contains charge carriers. The space between two depletion region is available for conducting portion of the channel where the bias voltage is applied externally to the gate. The reverse bias will increase will increase the reverse bias will increase and hence increase the penetration of the depletion region, which reduces the width of the conducting portion of the channel. When the width of the conducting portion of the channel reduces, the number of portion from source to drain reduces and the current flowing from drain to reduces. When the external reverse biases voltage at the gate is increased as shown in figure B and C, the depletion region will increases more and at a particular stage the width of the depletion region will be equal to the original width of the depletion region will increases and more and stage will come when the width of the depletion region will be equal to the original width of the channel, leaving zero width of the conducting portion of the channel. As shown in figure C, this will prevent any current flow from drain to source, and current this will cut off the drain current. The gate to source voltage that produces cutoff is known as cutoff voltage. When the gate is shorted to source, there is maximum reverse bias between gate and source p-n junction, making depletion region width maximum and conducting channel width maximum. In this case, maximum drain current flows, which is designed by IDSs, and this is the possible drain current in JFET. It is clear that the gate to source voltage controls to the current flowing through the channel, and hence FET is also called voltage control current source. When the gate is shorted, the source there is maximum reverse bias between gate and source PN junction, making depletion region width maximum and conducting channel width maximum. In this case, maximum drain cutoff, which is designed by IDSS, and this is the possible drain current in JFET. It is called clear that the gate source voltage current controls the current flowing through the channel, and hence JFET is also called voltage control current source, and the cutoff voltage VGS of OFF bracket close and one side bracket close. When the gate is shorted to source, there is maximum reverse bias between gate and source PN junction, making depletion region width maximum and conducting channel width maximum. In this case, maximum drained current flows, which is designated by IDSS, and this is the possible drain current in JFET. It is clear that the gate to source voltage, the current flowing through the channel, and hence FET is also called voltage control current source characteristics drain or current voltage characteristics of JFET. The current voltage characteristics of an NJFET is shown in the figure. The drain current ID is plotted with VDS for different values of VGS. The characteristics is also known as drain characteristics of JFET. From the figure, we can see that the voltage increased from 0 to a few volts. The current increases and determined by Ohm's law. The becomes a more horizontal and ID maintenance and a saturation level for VGS equals to 0 volts. The saturated value of ID is designated as IDSS, which is the drain to source current with source gate short circuit. Thus the IDSS is the maximum drain current for a JFET obtained under the conditions VGS equals to 0 volts and VDS VP. As the VDS increases beyond VP, the level of ID remains essentially the same, and this region of the characteristics is known as saturation region. It may also be noted that one of VDS VP, the JFET, has the characteristics of a current source. Thus, the current voltage characteristics displayed in figure can be divided into ohms, ohmic, linear, and saturation region with the bunch of conditions as the boundary. And this is the graph for the ohmic region. Conclusion: for turning on P-channel JFET, negative voltage can be applied across the drain terminal of the transistor W or T source terminal such that the drain terminals must be appropriately more negative than the source terminals. Thus, the current flows is allowed through the drain source channel. And thank you. And thank you.